This is section 2.2, the first of two videos. There's a lot in this section. We're going to talk about sets. George Cantor was the one who came up with set theory. It's really big. You used it as a child because you may have been playing with blocks and you learned to count your blocks, and you instinctively knew that the blocks on the left, you had less blocks than the ones on the right. Because a set is just a group of objects like the blocks in the previous example. Now, in this class, we want to be very precise with our language. So we talk about elements or members of a set. So notice we do the set inside braces, which are these, not to be confused with parentheses or brackets. So I could talk about the elements of set A. There are 5 of them, and I could list them for you. So we only list them once. The order does not matter. And if I think of what set A was the first 5 natural numbers. I could say things like 3 is an element of A. Or I could say 7 is not an element of A. And well-defined, we just know that we can tell if something's in the set or not in the set. Okay, we've been doing the roster method where we just list them. Notice here n, this is a set of natural numbers which start with 1 and they go off to infinity. There's an infinite number of natural numbers. Whereas set L, which it looks like this is the alphabet, there are 26 members in L. It's not infinite. It's finite. C is finite. There's only 4 elements in C. Okay, set builder notation. What's going on here? Well, I'll read it. The set E of all elements X such that X is an element of N, where N is the natural numbers, and X is less than 11. We use this notation because it's much more convenient than the roster method. In this case, E would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all the natural numbers that are less than 11. Okay, I'm going to play with these for a bit. Okay, over here, I'm going to call this set E, because those are the even natural numbers. And I'll call this set O for the odds. Well, if I want the evens, I can say the set of X such that X is an element of N, the natural numbers, and X is even. I could do O. O is the set of X such that X is an element of the naturals and X is odd. That describes both of my sets. But to be honest, this part isn't very mathematical. There's not a whole lot we can do with it, because I can't do algebra on it or anything. So I'm going to look at these in more detail. There's my set of natural numbers. I'm going to use little n as an element of the natural numbers. So n could be any of those. Watch how I write my even set now. Okay, it's the set X such that, now watch this, n is an element of the natural numbers, and X is 2 times n. This is much more mathematical. I can do algebra on that equation. And notice it does generate the even numbers. So when n is 1, X is 2. It's 2 times n. When n is 2, X is 4. When n is 3, X is 6. So I'm generating the natural numbers that are even. Okay, let's do it for odds. Okay, n is an element of the natural numbers. So the odd numbers are the set of X such that we're going to pull from the natural numbers. N is an element of the naturals. And X is 2 times n subtract 1. It's kind of thinking when you subtract from an even number. So if I have an even number and I subtract 1, I'm going to get an odd number. So watch this. When n is 1, X is 2 times 1 subtract 1 is 1. When n is 2, X is 2 times 2 subtract 1 is 4, subtract 1 is 3. When n is 3, X is 2 times 3 subtract 1 is 5. So I'm generating the set O of odd natural numbers. But in both of these cases, I now have statements here, equations, that I can do algebra on, and later on we'll use those to do some proofs. Okay, let's practice this. So A is the set of the elements 2k plus 1 such that k equals 3, 4, and 5. Well, my first element of A would be 2 times, I'm going to use k equals 3 plus 1 is 7. The second element of A, now k is 4, 2 times 4 plus 1 is 9. And the third element, I'll do k equals 5, 2 times 5 plus 1 is 11. So my set A are the 3 elements, 7, 9, and 11. Since we're talking about elements, we'll talk about equality. So again, the order of elements makes no difference. So if and only if, that means the converse is true as well. So if A is equal to set B, we write A equals B. That means they contain the same elements. So just very quickly. Yep. Let's do a very quick example of this. A equals 1, 2, 3. B equals 2, 3, 1. C equals 1, 2, 4. Well, since the elements makes no difference, we can see that A is equal to B. But now there's an element in C that's not contained in either of these, so A is not equal to C, nor is B. B is not equal to C. And that's the end of this first part of the section.